In this video, we shall discuss the cylinder. Now, let us assume that a certain curve C is given to us and a certain fixed line is given to us. Now what you do is draw a line through a point of the curve which is parallel to this fixed line. So let us say we draw a line parallel to this line passing through this point. Do that with all the points on C and look at the collection of all these lines. So what you get is a cylinder. This curve is called as the guiding curve. Each line is called as the generator. You can take any one line. So if you are thinking that way, it's like so suppose you take this line, the one passing through this point, and you move this line along this curve, always maintaining the line to be parallel to this fixed line. What you get is a cylinder. This fixed line, you can call it as the axis. Now please note that in the school days normally you referred to a cylinder to be a right circular cylinder, and it was an object of finite length. So the cross section of the cylinder was a circle of some fixed radius, and the cylinder was of some finite height. Whereas if you look at this, the definition which I have given, we don't even require the curve to be a circle. In fact, you don't even require it to be a closed curve. Here I have illustrated with the help of a closed curve. For a general cylinder, even that is not the requirement. And also, the axis may not be perpendicular to the plane of this curve, if at all the curve lies in a plane. The line is infinite in length, therefore this is an infinite cylinder. So one needs to keep these things in mind when one is discussing a cylinder in general. The requirement of the syllabus is to write down the equation of a right circular cylinder. So we are not going to work in this much of generality. We shall be writing down the equation of a right circular cylinder. That is what we will do next. We just had a look at the description of a general cylinder. So given a curve C, the guiding curve, one allows the generator to move along this curve, always remaining parallel to a fixed line which we call as the axis, and what we get is a cylinder. It's an infinite cylinder. Now we are going to write down the equation of a right circular cylinder. What I have here is a circle. This is our guiding curve. This is the center of the circle. I have not given a name to it. Maybe we can call it as capital A. I prefer to take the axis to pass through the center. So L is the axis and it is passing through the center of the circle. And since it's a right circular cylinder, the axis is perpendicular to the plane of the circle. The direction ratios of the axis are L, M and N. The radius of the cylinder. So what I've done is shown two generators. One is this line passing through P, a generate point on the generator, and there's another one here. So these are the two generators which I've shown in this diagram. Since it's a right circular cylinder, the radius of the cylinder and the radius of the circle is the same. So what I've done is I've taken a point on the generator and dropped a perpendicular on the axis. What I get is rho, the radius of the cylinder. Since the axis L is known to me, I can take an arbitrary point on the axis. So in order to be able to write down the equation of the axis, I assume that I know this point Q with coordinates alpha, beta and gamma on the axis. I join P with Q, and the angle that PQ makes with the axis is being denoted by theta. So PRQ is a right angle triangle. I make a note of that and apply the Pythagoras theorem to this triangle. PQ square is therefore equal to PR square plus RQ square or QR square. RQ is the projection of PQ on the line L, and therefore RQ is PQ cos theta. Theta is a variable angle because as you choose P on this line, it's obvious that the angle theta is going to vary. So I wish to eliminate theta from this equation. PQ can be found by using the distance formula. It will involve the generate point x, y, z and this fixed point alpha, beta and gamma. PR is a constant, rho. The projection is going to involve this theta, and I should get rid of theta somehow. Now what I do is look at a unit vector in this direction, and that is obviously Li plus Mj plus Nk divided by the square root of L square plus M square plus N square. If L, M, N are the direction cosines, then obviously the denominator is going to be 1. Otherwise what I get is LMN. If LMN are the direction ratios in general, then the unit vector in that direction will be given by this formula. I also look at a unit vector along PQ. I'm calling it as B cap. So if I look at the dot product of these two, so the dot product of A cap and B cap will be mod A mod B cos theta. But mod A is 1, mod B is 1, So what I have is just cos theta. So a cap dot b cap is cos theta. This is what I'm going to use in order to eliminate this. So the unit vector b, let me just calculate this, and the calculation is here. B cap is x minus alpha I, y minus beta j, z minus gamma k. X minus alpha, y minus beta, z minus gamma are the direction ratios of the line passing through PQ. Okay, x minus alpha, y minus beta, z minus gamma are the direction ratios. I create a vector out of that, a unit vector out of that. So I have x minus alpha I plus y minus beta j plus z minus gamma k divided by the magnitude of this vector, which is the square root of x minus alpha square plus y minus beta square plus z minus gamma square. Okay, and now I substitute all of these things into this equation. PQ square, which is the distance between P and Q, is x minus alpha square plus y minus beta square plus z minus gamma square. So that's what I have here. X minus alpha square plus y minus beta square plus z minus gamma square is equal to the radius square, rho square, plus PQ square cos square theta. QR is PQ cos theta. And cos theta is a cap dot b cap. This is the vector a cap, this is the vector b cap, and the square of that. So square of that. So what is the dot product of these two vectors? L times cos alpha minus beta, m times y minus beta, sorry, L times x minus alpha plus m times y minus beta plus n times z minus gamma, and the square of that. So theta is not there in this expression anymore. And what I have is an equation, quadratic, and this is the equation of the right circular cylinder. So that's all in this video. We stop with this. In the next video, I shall be discussing the equation of the right circular cone, and after that we will take up illustrations on how to work with the equation of the cylinder and the cone.